Okay. Well, um, let's see. Maybe I think we did an example last time. We'll have some examples where we calculate conditional probabilities. But in the text, it introduces a sample, a a box of sort of size 10 and 20, and where there's little eggshell buckets in here, so there's going to be 200 of them, and you toss a marble in and then ask for the probability that various events occurs. And so there were various events we I defined, like there's left and right, and then looking at it slightly differently, where there's 10 and 20, we did top and bottom, and also there was Q1, Q4, Q2, and Q3, and then there was also the middle, which was the middle equals Q2 union Q3. Okay, so and then lastly, and perhaps most importantly for understanding conditional probability, there was a diagonal. This was diagonal top, I think, and diagonal bottom. Okay, so the idea here is to look at the conditional probability of various different situations using this definition in this case. Well, let's just look at how some of these are all different events, and so we can look at the conditional probability in these different cases, and we'll come across the idea of independent and see which one of these events, which of these different events that we've defined are independent and which are dependent, and what that could mean. Okay, well, let's look at the conditional probability that it's in that the ball is in the left, given that it's in the right. Well, according to our definition, that's the probability of the intersection of left and right over the probability it's in the right. Well, that's going to equal, well, this is the empty set, because it either has to be in the left or the right. It can't be in both. So this is the probability of the empty set over the probability that it's R, which equals 0 over, you can see this is 1/2, because it's 1/2 this space. Okay, so that equals 0. Well, so if you know the right, if you know the ball was in the right, then you know it's not in the left. That's what this says. It's impossible that it's in the left. On the other hand, sort of the flip side of that is, well, let's say, what's the probability that it's in Q1? Oh, let's say, what's the probability that it's in the left, given that it's in Q1? Well, that's going to be the probability of the intersection of Q1 over the probability of Q1. Now, the curious thing about Q1 is this first quarter, it's a subset of L, that Q1 here as an event is a subset of L. So the intersection of the two, see, Q1 is inside L. So if I take things that are in Q1 that are also in L, that's just going to be Q1. So that's going to be the probability of Q1, the numerator, over the probability of Q1, which is going to equal 1/4 over 1/4, which equals 1. So if you know that a subset of an event has occurred, then it's absolutely certain that this event has occurred, because these are just special cases of the event that you're looking at. So these are two cases where the event that occurs in two different ways, where there's no intersection and a subset intersection, when what the probability that L occurs is strongly affected by which set you know has occurred. Now, so what we're going to do, what the definition of independent events is, if the probability of A given B equals the probability of A, that is, it doesn't matter that if you know that B has occurred, it tells you nothing about whether A occurs. Then we say, if this is true, then A and B are independent events. Okay, well, that's the definition of independent events.